Hi everyone and welcome to this my video on the general solution of trigonometric equations. My goodness, could it get any more exciting than this? No, not really. My name's Darren from Maths Guru. Thank you very much for joining me. Hopefully this video is going to be useful. It's part of the Year 11 Mathematical Methods course here in Australia, but don't worry about it if you've never heard of Australia or mathematical methods. It is fine because math is universal and solving trigonometric equations pretty much was everywhere I needed in the United Kingdom, and I'm sure all over the world as well. Now, if you can do me an honor of subscribing to my YouTube channel, that would be amazing. Why? Because nobody watches math videos. You're only watching this because you've had to. You know it, I know it, and I sit in a room talking to myself. So if you can do that, that would be great. Now, behind me are our learning objectives. Let's see what it says. Understand what it means to have a general solution for trig equations. Know how to find it from first principles and the idea of general solutions. To be able to find the general solutions and apply this understanding to a range of problems. Now, the range of problems, again, everything you do can be turned into an application style problem. So learning the theory that I'm about to show you is all well and good. Regurgitating it will get you so far. Understanding what you're doing and how we can apply this or use it in tricky questions, that's actually way, way more important. Now, I don't know about you, but in previous chapters or whatever else, I've ended up with situations like this here, where I've put into my calculator or the question said to me, find the solutions to the sine of x equals 0.5. Yes, or sine x equals a half or whatever. And merrily, I've gone along my way and I've put into my calculator, solve sine x equals 0.5 comma x, and my calculator's absolutely cracked it. You're like, what? Because suddenly I end up with this really strange thing. I've got like, what is n1? Huh? Now, if you did that on your calculator at the moment, there's no guarantee you would even get N1. You might get P1 or N347. I've got no idea. But even when I try, I'm like, okay, it might be a mistake with the sine thing. Maybe I'll try it with cos. And again, weirdly, I've got this here. I've got 6N2 minus 1. Now, you've obviously got way better teachers than I will ever be. And they'll have turned around and said, oh, that's a parameter. And you're like, oh, good, thanks for sharing. What is a parameter? Well, let's not rush things. Let's get into this at a moment. Now, let's start off by finding the general solution for cosine. Now, I'm going to say a specific example, and it's come from the Cambridge textbooks. Thank you very much, Cambridge, for letting me use your examples. You guys genuinely rock. I am so deeply grateful. Your textbooks are amazing. So we're going to start off with this here. We're going to try and find all the solutions for where the cosine of x equals 0.5. Now, if you understand what that means, we're trying to find all the points of intersection between the curve cosine of x and the line y equals 0.5. And to make things a little bit easier for you, here is a graph, one I created earlier on Desmos. Now, here we go. Here is my cosine curve. Very beautiful. And here is my line y equals 0.5. And because we are not regurgitating, we're trying to understand that we're trying to find those points of intersection. There we go. I've even highlighted the point of intersections for you. Ka-ching. Hold on a moment. Well, we know that the cosine curve, and Desmos hasn't done this, but I'm going to do it, goes to infinity and beyond. Why? Well, there's nothing here that's actually restricted my domain, right? Because the cosine curve goes from minus infinity to plus infinity, yeah, we actually have an infinite number of solutions. These aren't the only solutions. 1, 2, 3, 4, 5. Those are the 5 that could fit on my screen. There are loads more. Okay, so how do we find all of the solutions? Well, you can't. Trying to find all of those individual solutions would take you for a very long time. Yeah, and in an exam, highly unlikely. But what if we could find a formula that helped us find some or all of those solutions, or a way at least of finding them? So let's go back to the example I had a moment ago, and we're going to try and find the cosine of x equals 0.5. Now, when you do this on your calculator, the inverse cos of 0.5, if you've got your calculator in radians mode, it will always give you a solution. Now, hopefully it's going to be the one that's closest to the y-axis or the x equals 0 value, but you know, how the calculator comes up to it is magic as far as I'm concerned. But we now know from, what the calculator said is a solution one solution would be pi on 3. So what I'm going to do now is I'm going to put that on my thing, and I'm going to say, well, okay, I now know that's pi on 3. Because we're some way into the methods course, we know that there are other solutions in the unit circle that will have a cosine of equal to 0.5, right? And one of the ways of doing it is saying, well, if we look here, all stations, no, sine is positive in that quadrant, so that's no good because we've got a positive 0.5 here. Tan is positive, so it must be here. And again, through symmetry, I'm going to do that one there. I know that that's pi on 3. So one of my solutions is pi on 3. How do I find this solution here? Well, I know that's 0. That's pi on 2. That's pi. That's 3 pi on 2. And that's also 2 pi. So if I was to do 2 pi minus pi on 3, that would give me my other solution. Now, yes, I can work out what that is. But actually, I'm not going to. I'm going to leave it in the idea that there's pi on 3, my initial solution, and another one that I can find out by doing 2 pi minus pi on 3. Okay, so here we go. Here is my first solution is pi on 3, and I've got another solution at 2 pi on 3. 2 pi minus pi on 3. Well, how do we find all of the other solutions? Well, we know from our previous graph that cosine repeats every 2 pi. Right? We've done that to death in previous questions or previous exercises. So if we know it repeats every 2 pi, then what I'm now going to do is say, well, if I've got this solution here as pi on 3, to get to my next one is 2 pi plus pi on 3. Okay. And if I've got 2 pi minus pi on 3, to get to here, I'm going to add on another 2 pi. Well, 2 pi plus 2 pi is 4 pi. 4 pi, no, 4 pi, I'm not buying tissues, 4 pi. And there we go. So there are another 2 solutions. But how do I then get to the next 2 solutions? Well, I add on another 2 pi. And how do I get to the next solutions? Well, I add on another 2 pi, and I keep going ad nauseum. Now, obviously, this only deals with the solutions to the right, because theoretically, I could do 2 pi. I could do, what would it be? I could take 2 pi away. So it would be minus 2 pi plus pi on 3, or minus 4 pi. But let's not overcomplicate it. Right. Now, my brain, I don't know about you, starts to look for patterns. And I'm like, oh, hold on. There's a bit of a pattern here. If I take all of these values and shift them down, it's not changing the values. I'm just writing it in a different way. I suddenly start to see something quite interesting. Oh, look. 2 pi plus pi on 3, 2 pi minus pi on 3, 4 pi plus pi on 3, 4 pi minus pi on 3, 6 pi plus. What? This is awesome. Now, okay, I've got a bit of an interesting issue here because that doesn't have anything in terms of pi. Well, it can now because that's just going to be 0 pi. Ooh. Now, bearing in mind I've got 2 pi, 2 pi, 4 pi, 4 pi, 6 pi, 6 pi, I can now probably fill in my missing values here. And now that's going to be 0 pi minus pi on 3. And that's going to become 8 pi plus pi on 3. And now I have a beautiful pattern. Now, I'm going to take a bit of a break after showing you this screen, because we notice that there are, in fact, patterns. 0, 2, 4, 6, 8. Who do we appreciate? Maths guru. Okay, too much. 2, 4, 6, 8. They're my even numbers. Okay, well, we know from other stuff that we've done before, and hopefully a really good teacher, that our even numbers are basically expressed using the idea of 2n, where n is in my integers. Now, z basically are integers, and integers are whole numbers. They can be both positive and negative. So for any whole number, for any integer, we can basically get an even number. So if n is 1, 2 times 1 is 2. N is 2, 2 2s are 4. N is 3, 6. All right, so it doesn't matter what n value is, we will get our values of our even numbers. What about here? Well, again, if I make n equals 1, 2 times 1 is 2 plus 1 is 3. If n is 2, I get 4, 5. So 3, 5, 7, 9. So this creates my odd numbers. Now, how is that going to be useful to me? Well, let's now have a look at the fact that we've got even numbers, right? So we now know that we can get our even numbers by basically replacing it with 2n. So there's 0, 2, 4, 6, 8. I can replace all of these numbers here by 2n. So I've now got 2n pi. So there's 2n pi plus pi on 3. So all of these numbers here are created by using 2n pi plus pi on 3. Now, a word of warning, when you start using n's in this situation, you have to do the comma and you have to do the n is in the integers, right? Because otherwise it doesn't make any sense. So we've noticed now that we've got our even numbers of pi plus pi on 3. And on this side here, we've got our even numbers of pi minus pi on 3. So again, that 0, 2, 4 can be replaced with 2n. There's my pi. And we've got this minus pi on 3 again. So now we have two equations to help us find all the solutions for cosine. All of my general solutions for cosine. But I don't like two formulas. I want two formulas. I want one. Well, if we go back to the quadratic equation, all right, and I'll write it because I can, x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. You've actually met a notation before that is really helpful. The plus and minus on top of each other. Because if you remember, this really is nothing more than a way of writing two equations in one. It's helping us find two solutions, one with a positive and one with a negative. And so, what do we notice here? I've got a positive and I've got a negative. And so lo and behold, because my 2n pi is the same, because my pi on 3 is the same, and the only difference is that plus and minus, I can combine them to give me this. And again, don't forget the comma and the n in z, all right? Now, a word of warning here, because lots of people who then go away and do this and go, oh, it's always going to be pi on 3. It's always going to be pi on 3. No, it really isn't going to always be pi on 3, because that pi on 3 was very specific to cosine of x equals 0.5. So, for all general solutions of cosine, this bit here will be the same. That pi on 3 will be different, and it will be based on your initial solution that you got earlier. All right? Now, obviously, here, that's specific. We can replace this pi on 3 here with cos to the minus 1 of a. Now, you're going to turn around and say, where on earth did you get that from? Well, we had the cosine of x was equal to a half. So the x was equal to the cosine to the minus 1 of a half. Yes? That was the specific equation. Now, what if we make this here a? To take away the fact that that's a number, well, there we go. We get my initial solution, which is what that effectively is. My initial solution is the cos to the minus 1 of whatever this value here was. So we can take out that sort of pi on 3 or 0.5 or whatever it was. And here we go. I have just shown you how to find the general solutions to any cosine curve. Right? So again, my solutions are given by 2m pi plus and minus, so that will give me the two values each time, of the inverse cos of whatever that value there was, a half, root 3 on 2, or what have you. Cool. Right. Now, if we now look at the fact that we've got the general solution of the equation in this form here, can we write it in a different way? Now, I've said here better. It is actually just different. And the questions in the exam, and there are always questions like this in an exam, I promise you, yes, will actually expect you to write it in a particular form. So what I'm going to do now is take this and write it in a slightly different way. Right, well, first things first, we've got a numerator and denominator here. So what I'm now going to do is separate this so that it has a denominator of 3. Why? Because that's a denominator of 3. So I'm going to make my divide by 1 3 times bigger on the bottom, which means I need to make that 3 times bigger on the top. So 2 times 3 is 6. So these two are still exactly the same. All I've done is I've turned this into a fraction in terms of thirds. Right, well, now we know that where the denominators are the same, we can combine it into one fraction. So again, all I've done here now is written 6n pi plus pi, or plus or minus pi there, and I've combined the denominators to make it 3 there. And factorizing out my value of pi, ka-ching, there we go. We've got a nice, easy way of trying to find all of my solutions. Why? Because I can make n equals 1 now, and I can do 6 times 1 plus 1, 6 times 1 minus 1. And that seems to be a little bit easier than trying to do that. Now, a lot of people will disagree. Now, what I want to do now is go back and compare that with what we had at the start. Remember that very first screen where I'd put it in, I'd gone, solve the sine of x equals 0.5 equals x, and solve cosine of x equals 0.5. I now want to show you what your calculator spat out. Why? Because take out the n2 and just make it n. We've got 6n minus 1 pi on 3. Oh my goodness gracious me. 6n minus 1 times pi on 3. That and that are the same. And that are the same. So actually, your calculator, believe it or not, was trying to help you. Because when you don't put your domain in, he says, trying to actually get it to highlight, when you don't put your domain in, your calculator actually spits out the general solution for you. Yes, this is a parameter. It just means that that's a value that you get to change. Okay, so again, they've put n in here. That is nothing more than saying you choose your n value. If you want your first solution, which makes no sense really, n equals 0, 6 times 0 is 0, minus 1 pi on 3. So one of the solutions is minus pi on 3, or in this situation here, pi on 3. Now again, the question might say, find your first positive solution. Then we would know that it wouldn't be this one, it would be that one. But this is... What about tan? Well, actually, we can use exactly the same idea with tan. Really? Absolutely. So, starting with something nice and simple, let's look at tan of x equals 1. So, if we want to find then x becomes equal to the tan to the minus 1 of 1, which basically gives me pi on 4. Ka-ching! So, my first solution, pi on 4. For tan, how do we get to each successive solution? Well, we know that we add on pi, right? So if I had my all stations to Canberra business, I know that it would be in the third quadrant, and in which case that just means add on pi each time. So here we go. So let's just check I've got that. I've got my pi on 4 plus pi on 4 plus 2 pi on 4 plus 3 pi on 4 plus 4 pi, aha! There is a pattern again. So I've got 0 pi, let's actually just write that in. I've got 0 pi plus. So what have I got? I've got 0, 1, 2, 3, 4, 5. So this is actually easier, believe it or not, because my coefficients of pi are basically the counting numbers, 0, 1, 2, or more importantly, the integers, which we know we can replace with the idea of n in z. So now I know that all of my solutions for tan are given strictly by n pi, let's just check, n times pi, n times pi, n times pi, n times, yep, and then plus pi on 4. Now again, a word of warning, we've got to be very, very careful here because we know that that pi on 4 is that specific example where we had a equals 1, right? So pi on 4 was my first solution for that specific one. But as I say here, you've also got to remember that n can be negative too. And I have seen exam questions trick people by asking for the first 3 negative values, where you would use your n values as minus 1, minus 2, minus 3, and go on until you find the values that you actually need. So don't get tricked there. To then turn this into a general solution for tan, we therefore know that x, each individual solution is given by n times pi plus tan to the minus 1 of a. And again, just to explain where that came from, we had previously tan of x equals 1. If we take that value out there and make it some value of a, then x becomes equal to tan to the minus 1 of a, my initial solution, which is effectively what that there is. All right, so once I've got my initial solution, I add and take away multiples of n pi. Right, what about sine? Well, again, I'm going to overlabor this just a little bit because it's important to know, because sine is quite different. Sine has 2 formulas, believe it or not, all right, or 2 distinct formulas. So using the idea we had once before, what have we got? We've got here the idea that let's have our equation as sine of x equals 0.5. So when I do sine to the minus 1 of 0.5, I get pi on 6. Right, okay, so I'm going to draw on, again, just a random diagram of pi on 6. Where is that going to have another solution such that sine of x equals 0.5? My unit circle tells me that that will be also pi on 6. So pi on 6 here. Now, how to get this one is going to be pi minus pi on 6. Now that's going to be 5 pi on 6, as I've got here. But again, in the same way as we did it before, is this going to be helpful to know that it's pi minus pi on 6? Yep, well, there we go. So looking once again, first solution was pi on 6. To get my next solution was pi minus pi on 6. How do we get successive solutions? Well, much like the cosine curve, we know that sine repeats every 2 pi. So I'm now going to add on 2 pi to that solution. I'm going to add on another 2 pi to that solution and another 2 pi to that solution. Likewise, add on 2 pi, add on 2 pi, and add on 2 pi. What do we notice here? Well, our numbers, if we now write this as, let's write it in here, 0 pi plus pi on 6. On the left-hand side, we've got 0, 2, 4, 6. But we've met that before. That's my even numbers. And we know my even numbers can be expressed or replaced with just 2n, where n is in integers. Ooh, what about the right-hand side? What about these other solutions? I've got 1, 3, 5, 7. Oh, well, that's okay, because we know that the odd numbers can be expressed as 2n plus 1. So we now have a way of changing those into, and again, it's specific to the example we did before, 2n pi plus pi on 6. So again, there's my plus pi on 6. My 2n is coming from the 2, 4, 6, and my pi was there. Or 2n plus 1 pi minus pi on 6. And again, all of these were minus pi on 6. There's my pi. And the 2n plus 1 is just going to give me these numbers 1, 3, 5, 7. Now, unlike the cosine, can I combine these together? Sadly not. Why? Because that's 2n and that's 2n plus 1. And so ultimately, we actually have to leave those in exactly in the ways that we've got here. So he says one of the solutions now will be 2n pi plus sine to the minus 1 of a. And realistically speaking, that should be x is equal to 2n plus 1 pi minus sine to the minus 1 of a, if we were going to write that in the general form. I'll probably update that a little bit later on. Right, so there we go. Believe it or not, they are my general solutions, and they should go in your summary book, because who in an exam is going to sit there and try and work these things out, okay? Not me, I tell you that for nothing. Right, so find the general solution of each of the following equations. Okay, well, I know that we've pretty much done the first one already. Cos x is equal to 0.5. Now, if I was going to do this, I'd be firing up my calculator. Let's do a calculator screen. Please don't use the scratch pad, guys. It depresses the life out of me, all right? So I'm going to do solve. He says typing in the wrong thing. Solve. Trig. Cos to the minus 1 of x equals 0.5. Actually, I didn't need to do solve. I don't know why I did solve. No world of my own. Right. That's not particularly helpful, is it? Cos to the minus 1 of 0.5. Bearing in mind it says in radians. What is happening there? Let's go to settings and status, document settings. Let's put it into exact, hit enter. Is that going to give me the right answer now? Ooh. Making sure your calculator's in the right mode is always a good idea, I think. Right, so there we go. So I've got my initial solution, or in this situation, yeah, as what is it? Pi on 3. And I realistically don't need to do any more thinking, believe it or not, because I know that my cos is this one here. How do I know that? It's got cos in it. I know that there is my initial solution. So therefore, the answer to this gives me that x is equal to 2n pi plus or minus pi on 3. I'm going to write it in a different form just because I can. Remember, that can become 6 n pi on 3 plus or minus pi on 3, which gives me 6n pi plus or minus pi all on 3, which gives me, take the pi out, 6n plus or minus 1 divided by 3. Ka-ching! Now again, the exam may tell you which format to write it in. There's nothing wrong with either of those forms. I just, believe it or not, prefer that. I don't know. Now, believe it or not, the 3x is a bit of a trick. It builds on the work we've done before. Now, remember, what would we have done before? Well, I would have said that tan of 3x is equal to 1 on root 3. So 3x is equal to tan to the minus 1 of 1 on root 3. Now, believe it or not, that's what I'm going to do. I'm going to find my general solutions for 3x. I'm not going to try and do this by a third, although I can. I'm going to leave this at the moment in that way. So let's fire up my calculator, and let's do tan to the minus 1. So trig tan to the, oh, come on, play nice. Tan to the minus 1 of 1 on square root of 3. Hit enter, and we get pi on 6. Awesome. So we know that that's equal to pi on 6 as my first solution. I'm not going to write that. So we now know that 3x is equal. I'm going to write pi on 6 here just so I don't forget it. Now, where was tan? Okay, tan, nice and easy, was that one there. So I now get 3x equals n pi plus tan to the minus 1 of 8, which was pi on 6. Okay, right. So now, having got that, I'm going to divide everything by 3 to give me that x is equal to n pi on 3 plus pi on 18, making that 6n pi on 18 plus pi on 18 gives me all on 18. So I get 6n pi plus pi, which gives me pi, lots of 6n plus 1 on 18. Easy, really? All right, and he says, what about this one? Sine x equals root 2, or 2 sine x equals root 2. So 2 sine x is equal to root 2. Sine x equals root 2 divided by 2. So my first solution, what am I going to do? Well, I've got my calculator, so let's do that. Trig sine to the minus 1, if you will, please, of root 2 divided by 2, oh, not 2, 3, gives me pi on 4. Now, there's probably lots of people there shouting at me going, of course it's pi on 4. Don't you remember these things? No, not really. So we've got pi on 4. So therefore, we get that my general solution is going to be x is equal to, now remember for sine there are actually 2. There's that one there, and there's that one there. So my x is going to be given by 2m pi plus pi on 4. And x is going to be given to 2n plus 1 pi minus pi on 4. Now again, we can make these simpler, but not to blow out the length of this video any longer, because that's about 28 minutes so far, and I've got some 3 more examples to do. You can go away and do that. In fact, I do it for you. Right, here we go. Now, how can we use this to then go one step further? Find the first 3 positive solutions of each of the following equations. Now, having done all of that hard work, we've actually repeated the questions, and what I've done here is written down our solutions. So find the first 3 positive solutions. Now, a lot of people get a bit tricked here with like, well, what's the value of n? Believe it or not, start with 0 and see what happens then, okay? So when I put n equals 0 in here, so, and I'm just going to write n equals 0 here. I'm going to get my values of x is equal to, well, 6 times 0 plus 1 is going to give me pi on 3. And 6 times 0, which is 0, minus 1 is minus 1. So it's minus pi on 3. So I'm going to discount that for the moment. Don't need it. Is it worth going negative? Well, if I make n equals minus 1, I'm going to get loads of negative values. So my next value I'm going to try is n equals 1. That's going to give me 6 plus 1, which is 7. So x equals 7 pi on 3. And 6 minus 1 gives me 5 pi on 3. And believe it or not, I'm done. I don't need any more because I've got my first 3. So therefore, I would write down that x gives me equal to, what is it? Pi on 3, 5 pi on 3, and 7 pi on 3. Ka-ching. Job done. What about the next ones? Well, what have we got here? So I've got my general solution again. So now we're trying to find all of my first 3 positive solutions here for for what? Tan of 3x equals yada, yada, yada. Right, so let's choose n equals 0 first. What do I get? 6 times 0 is 0, so I get pi on 18. Only one solution there. What about n equals 1? So I'm going to get 6 plus 1 is 7. So we get 7 pi on 18. N equals 2 gives me 12, 13 pi on 18. Now, again, I always tend to check with a negative just in case. minus 1 will give me minus 6 plus 1 minus 5. Nope. And so in which case I'm hoping my solutions are therefore x is equal to pi on 18, 7 pi on 18, and 13 pi on 18. Now again, notice how I always list them separately. I want to answer my question so that I don't get tricked. Oish! Find the first 3 positive solutions of each of the following equations. Right, now this is the one with sine. Sine's always the trickier one, and I can guarantee you in an exam, the chances are we're going to give you sine because it's going to test your understanding. So let's have a look. We're going to work out for the first equation. So let's say x, let's say first thing, so we'll say n equals 0. So when we got n equals 0 for that one there, we got 8 plus 1, or 0 plus 1 is 1. So we get x is equal to pi on 4. And when n equals 0 for the next one, all right, so again, n equals 0, we've only got one solution here. N equals 0, what are we going to get there? So we're going to get 3 pi on 4. What about n equals 1? We're going to get 8 plus 1, which is 8 plus 1 is 9. So 9 pi on 4, and 8 plus 3, 8, 9, 10, 11. 11 pi on 4. Now again, I'm just going to check minus 1 just to make sure I'm not going to get tricked. If I try minus 1 in here, that'd be minus 8 plus 1, which will be negative, minus 8 plus 3, which is negative. And so actually, I've got my first 3 values. So therefore, x would become equal to pi on 4, comma, 3 pi on 4, and 9 pi on 4. Ka-ching. We are done, I think. Pretty much so. Well, those are my learning objectives. Let's just tick off that we've worked them. Understand what it means to have a general solution for trig equations. Yes. Know how to find them from first principles. Yep. Be able to find the general solutions. Yep. And apply this understanding to a range of problems. Again, most of the exam questions I've seen are very much the type I've just gone through. All right, it'll be an algebra style question. Find the general solutions of these. There's nothing to be gained too much from doing application style questions on this. Not that I remember anyway. If you can subscribe to my YouTube channel, that would be massive because nobody watches maths videos other than you. And I'm not even sure you've made it this far. There are more videos coming. Thank you very much for watching. Hopefully you found it useful. Spread the word if you can. And hopefully I'll see you in another video. Until then, take care. Bye-bye.